Hi everyone, I am glad to be here and warmly welcome you all to my presentation on performance improvement of rail track ballast using geosynthetic and rubber under direct shear loading. First of all, I would like to convey my gratitude to the third International Conference in Geotechnical Engineering for giving me this great opportunity. I am Venuja. I am a research assistant at Faculty of Engineering, University of Peradeniya. Ballast is a coarse and highly angular material with high shear strength and bearing capacity. Ballast layer transfers the loads exerted from moving trains from sleepers to the underlying layers through wider area, therefore at a minimal level. With the time, due to the repeated cyclic and impact loads from the moving trains, ballast particles undergo breakage and the voids in the ballast layer clogged with broken particles. Ballast degradation and fouling leads to loss of shear strength and bearing capacity of ballast layer, therefore differential settlement, and it leads to poor drainage and it creates safety issues. Therefore, there is a need for frequent inspection and maintenance activities. I'll move on to the commonly used techniques to improve the performance of ballasted rail tracks. Rubber pads and geosynthetics are widely adapted artificial inclusions. Rubber pad increases the contact area, therefore it distributes the load through wider area, and also it provides soft interfaces between various components of ballasted rail tracks. GeoGrid reduces the lateral movements of ballast aggregates through mechanical interlocking and it acts as a tensile element, therefore it reduces the subgrade stresses. This research aims to analyze the effect of rubber pad and geogrids on the shear and deterioration behavior of ballast. The flowchart shows the methodology of this research. Initially, materials were collected. After that, ballast was sieved using 20, 25, 37.5, 53, 50 and 63 millimeter sieves to get the samples in each sieve interval according to the Indian standards. After that, ballast was cleaned using clean water. Then it is mixed based on IS standards. After that, ballast was prepared in 3 layers and each layer was placed into the apparatus to obtain the field unit weight. After that, the normal load was applied using a lever arm system. Then the constant shear displacement was applied to the bottom part of the shearing apparatus. After that, outcomes were extracted and the results were analyzed. These photographs shows the test procedure I explained in the previous slide. This is the test apparatus used in this study. This was designed and constructed at Geotechnical Laboratory. The apparatus can accommodate 400 millimeter diameter and 300 millimeter height of test sample. The normal load is applied using a static lever arm system, and a hydraulic jack is used to apply the shear displacement to the lower cylindrical part, and load cell is used to get the shear load from the test. Horizontal and vertical displacement gauges were used to extract the shear and vertical displacement of this test using a data logger. This graph shows the shear stress behavior of all kind of samples with different normal loads. With the higher normal loads for all samples, the shear stress increased. This is due to the higher interlocking of particles at higher normal loads. Therefore, there is a improvement in frictional resistance of ballast particles. The highest shear stress was obtained for fresh ballast compared with the artificial inclusions, but ballast with USB, UBM, and geogrid showed comparatively closer shear values that of fresh ballast. This is due to the particle interlocking behavior of geogrid. Therefore, it gives more frictional resistance to the shear loading. The figure 6 shows the peak shear stress variation of all samples. I'll move on to the breakage behavior of ballast. Ballast undergone to corner breakage, splitting and grinding due to the application of shear and normal loads. Ballast breakage can be calculated using the ballast breakage index formula suggested by Navaratnarajah et al. For each samples at higher normal loads, higher BBA was obtained. This is due to the higher compressing of samples, which reduces the dilation, so more particles undergo breakage. Lower BBI for ballast with a combination of USB and UBM was observed because there is a uniform stress distribution from USB inserted ballast. Therefore, there is a reduction in BBI, and also resilient rubber pads acted as cushion to the ballast. Therefore, there is a reduction in ballast breakage. Figure 7 shows the BBI of samples in the mean of layers. When compared with the top, middle, and bottom layers, middle layer showed higher breakage. This is due to the shear plane is at the middle of the shear apparatus. That brings me to the conclusions of my presentation. Artificial inclusion and normal loads have a significant effect on shear and breakage behavior of ballast. Shear stress increased with normal stress. This is due to the high frictional resistance resulted from the improved particle interlocking at higher normal loads. Fresh ballast had highest shear stress and friction angle compared with the ballast with artificial inclusions. On the other hand, ballast breakage was less for ballast with rubber and geogrid inclusions. Therefore, it is recommended to use a combination of rubber pad and geogrid in rail tracks from this study. I would like to thank a head grant by World Bank and University of Peradeniya research grant for the financial support provided to this study. And thank you so much for your interest and attention. And I would now be interested to hear from you with your thoughts and questions. Thank you.